Well, I don't know in abstract proof, I don't think. It looks like there's no trace, and specialists in von Neumann algebras assure us that there's nothing essential that we don't know there. But we did not prove in class there's no trace. We just observed that we didn't see how to find a trace. Well, yeah, okay. I can give a slightly better answer than that, though. We had the tensor product of two Hilbert spaces, and then we had a cyclic separating vector in there. And you see, you have to ask what operators we allow. So there's a small algebra of operators that only act on finitely many qubits. Well, that has a trace, more or less trivially. In other words, if an operator acts on n qubits, no matter which n qubits there are, you define its trace to be its normal trace in the Hilbert space of those n qubits, but you divide by 2 to the n. You need to normalize it this way because you have to use different n's for different operators. So that's the unique trace on A naught. So if then we complete A naught to a bigger algebra A. That depends on the state. Why do we take that completion? Because that gives an algebra that's intrinsically associated with the state and doesn't depend on how we approximated the system by a finite set of qubits. So in quantum field theory, for example, well, you could argue about a lattice system. But in quantum field theory, although you can approximate a system by a finite set of qubits, there's no canonical way to do that. So for each such approximation by finite many qubits, there would be a trace where there would be different traces for different algebras and different traces for different regularizations. If we want to do something which is intrinsic, we have to take the completion. And the completion gives us sort of all operators on which this function is well behaved. So okay, but once you do this, you're building in the density matrix of the state, which is a thermal density matrix. And only when the density matrix is a multiple of the identity is there going to be a trace on the completion. Okay. I have to admit, I finished that argument in an unconvincing fashion, even to me. But I'm groping around for what the correct argument is. So the basic problem is that for the approximation by qubits, there was a trace. But there was no canonical version of that. And the fact that it was, for each such approximation, the trace was uniquely determined. The fact that they disagree means that overall there's no trace. That's closer to being a good explanation, but I still feel it's short of a good explanation. Any other questions? Okay, so I guess we'll get started even though people are still coming in. So we're going to go back to quantum field theory. Well, we were mostly doing statistical mechanics last time. And so we can, in my picture now, time is vertical, space is horizontal. We consider an open set U, and I could also, for good measure, add the space-like separated open set V. And what we've discussed is that there's no decomposition of the Hilbert space. And therefore, there's no density matrix rho U or rho V, or a von Neumann entropy. So neither density matrices nor anything that depends on a trace is going to be a good definition in quantum field theory. So we only have algebras for the regions, not Hilbert spaces. So what are we going to do about this? Well, there are really two answers. We can look at linear combinations of entropies. Of entropies, for example, or other functions. In which UV divergences cancel. And hope to make true statements. And in practice, this is very important. In practice, this gives important and correct results. Though if you talk to mathematicians who work on operator algebras, you'll discover that they're considered non-rigorous. The reason they're considered non-rigorous is that in practice, there's no UV cutoff in the presence of which all the steps are correct. Nevertheless, there are important results obtained this way, quite a few, and I'll give one example next week. But today there's something else we'll do. I'm going to explain that although entropy isn't well defined, in QFT, relative entropy is. So, if psi and phi are two global states, that just means vectors in the Hilbert space of the world, which is the only one that we have, since there's no Hilbert space for the separate regions. We can define, and I'll explain how to do this, a relative entropy between the two states in region U. And in a way that will become clear, it's a good generalization of relative entropy in ordinary quantum systems, as we've defined it previously. However, before doing that, it's useful to give a slightly different definition of relative entropy in ordinary quantum systems. So the definition we gave in ordinary systems was this. We have a system A with Hilbert space HA, and we have two density matrices. Let's say rho and sigma. They're both map AJ to itself. They're both positive self-adjoint operators of trace 1, or density matrices. Then we define the relative entropy between rho and sigma as the trace of rho times log rho minus log sigma. And we actually introduced it as a naive generalization of the classical notion, where for the classical notion, we gave a good motivation in terms of measuring how easily you can prove that a wrong hypothesis is actually wrong. Now, another equivalent definition is as follows. So, add another system B. It could be a second copy of A. Such that there are vectors psi and phi in HA tensor HB that purify rho and sigma. So rho is supposed to rho, which I'll now call rho A, is supposed to be the density matrix on A in the state psi. So rho is the trace over B of psi, of the projection operator onto psi, and sigma is supposed to be, well, sigma, which I'll now call sigma A, is also the trace over B of psi psi. Is there a question about that? Oh, sorry. Thank you. Okay. Now, in this situation, we can also introduce rho B, which is the trace over A of psi psi. And something we know about this situation is that rho A and rho B have the same eigenvalues. So, the trace of rho A log rho A is the same as the trace of rho B log rho B. So an equivalent definition of relative entropy, except I'm now going to call it S of rho A relative to sigma A rather than rho and sigma. So, well, the original definition was the trace over HA of rho A log rho A minus log sigma A. But we can rewrite it as one term is the trace in HA, and we'll write the other term as a trace in HB. I haven't really changed anything because the part of the term that only involves rho could be just as well taken as a trace in HA or as a trace in HB because the two traces are equal by this statement. But we can rewrite this as follows. It's the expectation value in the state psi of, well, psi is in this big Hilbert space, HA tensor HB. So neither sigma A nor rho B is an operator on this big Hilbert space. What is such an operator is 1 tensor log sigma A, log sigma A tensor 1 on B. But there's also 1 on A tensor log rho B. All that I did, by putting in the 1s, I promoted log sigma A and log rho B to operators on this bigger Hilbert space. And now, to see that the statement is true, well, okay. Let me, for example, just manipulate one of the terms. This is equal to the trace over HA tensor HB of the pure state density matrix times log sigma A tensor 1B. But now we can simply do the trace over HB. The only operator acting on HB is the identity, so it doesn't do anything. And taking the trace turns psi into rho A. So this is the trace of rho A log sigma A. So you show that this is equal to that by taking the trace over B. Except that I missed a minus sign in front. And then you show similarly that this is equal to that by taking the trace over A. So we have an alternative formula for the relative entropy. And we can sort of trivially rewrite this in a minor way. Well, the reason I want to rewrite it is that neither term is well defined in quantum field theory, but the difference is well defined. So I want to sort of combine them together. Sorry, but I misspoke there. That's rho, not sigma. So this is an alternative formula for relative entropy in ordinary quantum mechanics. You introduce a so you'll notice that the formula, even though in the explanation I introduced both psi and phi, the formula only used psi. So we introduce a purification psi of rho, and then if the purification lives in HA tensor HB, we introduce this operator that acts on HA sigma A tensor rho B inverse, mapped HAB to itself. And we're able to express the relative entropy just in terms of the purification and also this matrix, sigma A tensor rho B inverse. So why is that useful? It's useful because things like sigma A or sigma A tensor 1 don't generalize to quantum field theory. But sigma A tensor rho B inverse does. In other words, there's a well-defined operator on the Hilbert space of a quantum field theory, and I'll tell you in a little bit how to define it, which in an ordinary quantum system reduces to sigma A tensor rho B inverse. So I'll call that operator, well, we'll call it later delta psi phi, will be the generalization. I won't say it's equal to, okay. For a situation where there's no factorization in quantum field theory, we'll nevertheless find an operator that plays the role of sigma A tensor rho B inverse. And when we find that operator, then we'll be able to define relative entropy in quantum field theory. So we'll define the relative entropy between states psi and phi in the Hilbert space of quantum field theory for a region U. So region U has an algebra A sub U, and the definition of delta psi phi, I'll call it delta psi phi of U. Given the pair of states and the region, will define an operator. And then the relative entropy between psi and phi in a region U will be defined by imitating the formula in ordinary quantum mechanics. So what I said is quite a mouthful, but the idea is just that although in quantum field theory, so the A and B systems correspond to U and V. in the quantum field theory context. Let's say A corresponds to region U. B will correspond to the space-like separated region V. And then there will be no sigma A tensor 1 or whatever, but this delta psi phi operator generalizes to arbitrary algebras, sigma A tensor rho B inverse. And since sigma A, unfortunately I seem to have erased the formula, but since sigma A tensor rho B inverse is all we need to define relative entropy, that will mean that relative entropy is a meaningful notion in quantum field theory. And for example, we'll see that knowing that enables us well, I hope to get there Tuesday, we'll see that, but anyway, at some point we'll see that knowing that is sufficient to get us to the Bekenstein bounds. So any questions before we go on to explain how to generalize sigma A tensor rho B inverse to quantum field theory? Okay. So we just need the basic definitions of what's called Tomita-Takasaki theory. So we have a Hilbert space H, and then we have a state in this Hilbert space, and an algebra A, which for us will be the algebra of a region U, or maybe the region V, or some region in space-time. A is an algebra that acts on H, and psi, we'll assume, is cyclic separating for A. So for example, A could be the algebra of a region in quantum field theory, and psi could be the vacuum state. And then we define the Tomita operator it's an anti-linear operator that takes H to H. It's defined as follows. For A in the algebra, S, well, I'll call it S psi. It's an operator whose definition depends on the choice of the state psi. Maps A psi to A dagger psi. Now, to make this definition well defined, it's well defined because psi is separating. So A psi is non-zero for all A. You see, if A psi could be 0 without A dagger psi being 0, this definition would be impossible, would be a contradiction. And S psi is densely defined because states of the form A psi are dense. Remember, in the proof of Riech-Schlieder, we showed that states gotten by acting on the vacuum with an operator in a specified region, those states are dense in Hilbert space. So this is a densely defined operator, but it's unbounded, meaning it's not defined on all vectors. I'll actually make a technical improvement in the definition a little bit later. But we're going to use the simplest definition, which I've given, for as long as it's enough. So it's somewhat analogous to the Hamiltonian of a typical quantum system. So p squared plus v where V is a potential and P is the momentum operator, is an unbounded operator, so it's densely defined on Hilbert space. It's not defined on all Hilbert space vectors. And likewise with this one, because we proved that A psi is never 0, but we didn't prove, and it's not true, that, you see, part of the Tomita-Takasaki theorem is that in a region, you can't define an annihilation operator. Because if you compel the support of a function to be in a given region, you can't make it only have positive or negative frequencies. But you can come very close to positive or negative frequencies. So you can have a situation where A is almost an annihilation operator, while A dagger is almost a creation operator. Therefore, A dagger psi can be much bigger than A psi, and S is an unbounded operator. So it has a few obvious properties, like S psi squared equals 1, and S psi of psi is equal to psi. Then we introduce what's called the modular operator. Delta psi, which is just S psi dagger S psi. Except I feel that definition needs a little bit of explanation because you're all familiar with the adjoint of a linear operator, but I at least always find it hard to even remember the proper definition of the adjoint of an antilinear operator. So I'm going to write down the definition of S psi dagger, or in general. So if W is antilinear, then the definition of W dagger is such that for any states in our Hilbert space, lambda, matrix element of lambda between W and chi, well, for a linear operator, this would be the definition. But for an antilinear operator, you complex conjugate it. So that's the definition. And you can get rid of the complex conjugation by reversing the order of the two states. So that's another version. So, well, the equivalence of the fact that either of these two is equal to this is the definition of what we mean by the adjoint of an antilinear operator. And given that, we can define delta psi. And delta psi is actually self-adjoint, well, and non-negative. Well, you see, for linear operators, you would know that if S were linear, you would all know that S dagger S is self-adjoint and non-negative. The purpose of the bar in this definition is to make it also true for the case that S is antilinear, that S dagger S is self-adjoint and non-negative. Perhaps I'll let you check that as an exercise. So maybe there should be a homework problem. So as an exercise, it verifies that delta psi is equal to or greater than 0 and self-adjoints. Well, I'll say Hermitian. So, hopefully it's clear from what I've said that this definition must make sense in quantum field theory. All we needed was a Hilbert space, a state, and an algebra acting on the Hilbert space. So in quantum field theory, we've got those. Now, the state had to be cyclic separating, but if there is any cyclic separating state, then any generic state is cyclic separating. So we proved in quantum field theory the vacuum was cyclic separating, but actually it implies that a dense set of states are cyclic separating. So we have a lot of freedom to do this in quantum field theory. So we define something in quantum field theory, but what is it? So, so I claim, well, first of all, I only introduced one state psi, so there was no two states psi and phi in this definition. We will generalize it in a bit. But I claim delta psi generalizes rho A tensor rho B inverse. So in other words, so if we had a splitting of the Hilbert space, which we don't, then we'd have density matrices rho U and then we would have an operator rho U tensor rho V inverse. So if we had a splitting, we could define rho U and rho V separately, and also we could define this operator that takes H to itself. And since it is an operator on H, it requires no choice of splitting. It doesn't require the existence of a splitting. When I say that delta psi generalizes rho A tensor rho B inverse, what I mean is that for a finite dimensional quantum system, if we used exactly these definitions, we would discover that delta psi is rho A tensor rho B inverse. Yes?
Why does the choice of splitting come into this definition?
Oh, sorry. It wasn't the choice of splitting. We needed a splitting. So no. The whole point of this is that there was no splitting here.
Oh, good. Yeah.
So this is always well defined.
Yeah.
Okay. So it was a simple definition, and it manifestly is well defined in quantum field theory. I claim, though, that if there had been a splitting, delta psi, you could show that delta psi is rho A tensor rho B inverse. We're going to calculate that in a second.
Oh, okay. Well, then I'll go back to the first.
Sorry. Okay. So I defined something, but from the definition, although it was simple, it's not clear what we've defined. The point of the definition, at least for our purposes, is that this operator generalizes rho A tensor rho B inverse. So we will have a generalization to quantum field theory of rho A tensor rho B inverse, though not of either rho A or rho B inverse separately. So how do we get that? So we go to an ordinary quantum system. So the system is AB, and psi, well, we know we can put psi in this form. To have a cyclic separating vector in ordinary quantum mechanics, the dimensions of the two systems have to be the same. People often say that the B system is a copy of the A system. More canonically, it's the complex conjugate. But anyway, then psi can be put in this form. And we're just going to calculate delta psi. Well, we're going to calculate what is S psi dagger, and then delta psi. And there's no mystery in any of the calculations because it's just a manipulation with finite matrices. And so we're going to work directly from the definition, which was this. So let A that acts on the HA system be such that A on the state I of the A system is the state J of the A system, and A on the state K of the A system is 0 for K not equal to I. So you see, what have I done here? I picked a very simple operator, but as you run over all I and J, operators of this form are a basis for the space of all operators on the Hilbert space HA. So we can completely characterize the operator SI by implementing this formula for operators of this kind. So, so first of all, if A does that, then A dagger does the opposite. So using those facts, we discover, well, the facts we're going to use are this. This is fact 1. That's what the state is. This is fact 2, how A acts, and fact 3 is how A dagger acts. Oh, sorry. Fact 2 is this, how A acts. Well, sorry. 2 is this, the combined statement. So A on psi is A on the sum of ck times k of A tensor k of B. But A annihilates all the terms where k is not equal to I. And it turns that term into j. So this is ck times I of A, j of A tensor I of B. Oh, thank you.
And the reason why I don't think about A is just because the characterization is symmetric with B5.
Well, in quantum field theory, we're trying to, to define the modular operator, we picked an algebra in quantum field theory. So the algebra in quantum mechanics will consist of all operators that act on A.
Okay.
We could have considered all operators that acted on B. Just like in quantum field theory, we could consider either region U or region V.
So delta U or A.
In either the quantum field theory or in the finite quantum system, we pick one of the two subsystems. Okay, hopefully we got that right now. And then we can similarly compute A dagger on psi. That's A dagger on the sum of ck times ka tensor kb. And so what is that? Well, A dagger selects the term where k is equal to j and maps it to I. So that's going to be I, A, tensor, J, B, times what? Cj, I guess. Is that right? Okay. So now we use this formula. So then we see S psi acting on A psi, which is this. Is equal to Cj on Ia tensor Jb. Well, we can pull out the Ci, but when we do that, we have to remember that S is antilinear. So S psi of Ja tensor Ib is Cj over Ci bar times Ia tensor Jb. So this gave a complete description of Si because I told you what Si did on every basis vector of Ha tensor Hb in an obvious basis. Now, hopefully I didn't erase the definition of the adjoint of an antilinear operator. Maybe I did. That's a pity. The adjoint operator, well, you see, Si exchanged the labels J and I. So the adjoint operator is going to exchange them back. But it's confusing what the C number multiplying it is going to be. it's Cj bar over Ci times Ja tensor IB. So, I mean, to get that formula, all you do is you take the adjoint of this operator. The only thing is that, as I've said a couple times, the definition of the adjoint of an antilinear operator is confusing. So, at least for me, it takes a little thought to decide whether the coefficient here is going to be this or its complex conjugate. Although a shortcut for getting it right is from the fact that S dagger S is self-adjoint. So, if we now take S dagger S, I possibly should have called this, okay, this was SI, but I could have called SI for the A system to build the algebra into the definition as we do in quantum field theory, or as I did in the general definition, wherever it was. So no, so I'll mostly leave it out and understand that we're acting on the A system. So once you know S psi and also S dagger psi, you can compute S dagger S. And S dagger S, what's S dagger S on J tensor I? Well, on the labels, J and I get flipped, but then they get by S, but then they get flipped back by S dagger. Then S multiplies U by a C number. And since S dagger S is going to be complex positive and self-adjoint, S dagger S has to multiply U by the opposite C number. So this is just Cj absolute value squared over Ci absolute value squared times Ja tensor Ib. So we got an easy formula for delta psi. Well, on a complete basis of states, we've computed the action of delta psi, which is the same as S dagger psi, S psi dagger S psi. But I claim that delta psi is rho A tensor rho B inverse. Well, why is that? Well, we'll just calculate rho A or rho B. Rho A is the trace over B of psi, and that's the sum of ck squared times the projection operator onto k. And rho B is the trace over A of psi, and that's the sum over k of ck squared times These are all A's because we're constructing an operator on the A system. And here we'll get all B's. So rho A and rho B are diagonal on this basis with eigenvalue, absolute value of C squared. But in our formula for delta psi, we multiplied the A state by C squared, and we multiplied the B state by the inverse of C squared. So overall, we've multiplied by rho A tensor rho B inverse. So we've discovered that rho A tensor rho B inverse, or an operator that generalizes rho A tensor rho B inverse, will be universally defined whenever you have an algebra acting on a Hilbert space. And therefore, it will be well defined in quantum field theory. Even though rho A and rho B themselves only make sense for algebras of type 1 or type 2. Now, any questions on that? Yes?
Is there an example that we should keep in mind, like for H finite dimension, like some state over integral?
Well, a finite dimensional example could be anything. What I was going to do in a moment was to give an example in quantum field theory. So you could verify an example where you can check more directly that rho A and rho B don't exist, but the tensor product of one with the inverse of the other does. Any other questions?
For
Yeah, well, you can modify the definitions for the case when it isn't invertible for the applications, but it would be longer. So in my explanation, we're assuming, well, I started by assuming the state was cyclic separating, and that implies that the density matrices are invertible. I don't want to give the generalizations in the non-cyclic separating case. Any other questions? Yes?
Do you know any resources for the non-cyclic separating case that I agree?
Do I know any references?
Yes.
Well, I have to apologize for this, but I recommend my own lecture notes. I recommended them on Tuesday. I'm talking about, well, these definitions and this computation are in section 3 of those lecture notes. No, the one which is the one I recommended on Tuesday. Well, the one I told you to read for today, which is called Notes on Some Entanglement Properties. Okay. Sorry.
Did we maybe get the complex conjugate in that coefficient?
Which one?
The definition of the action of SI dagger on here on the left one.
Well, we didn't compute it in class. I just wrote it down.
SI dagger is antilinear, right?
As is SI.
Sorry.
As is SI.
So then it seems.
You have to use the definition of an antilinear operator, of the adjoint of an antilinear operator. The definition of the adjoint of an antilinear operator has an unfamiliar complex conjugation. If you use that definition, you'll get this answer. But as I said, a shortcut is the following. The definition of the adjoint of an antilinear operator is made so that S dagger S is positive, whether S is linear or antilinear. And therefore, if S gives this C number, S dagger will give the complex conjugate C number, which is what I've written here. We didn't check it from the definition of an antilinear operator, but it will work if you check it.
If I act with SI dagger on this expression here, that will turn CJ's CI bar into CJ bar CI, right? Because it's antilinear.
Yes?
And then.
Sorry. You're right, actually. Thank you. Well, let me check what I have in my notes, if you don't mind. Yeah, this is correct. What he said is correct. This formula is correct. But the way we get that formula is that SI produces this factor, and SI dagger acting on the basis state would produce the same factor. But we don't want SI dagger to act on the basis state. We want it to act on SI of the basis state. Then, if you pull this factor through SI dagger, it will get complex conjugated. So this, which actually is what I had in my notes, I tried to shorten the lecture. My notes actually have a duration, but I tried to shorten the lecture by just writing down what the answer had to be. But I wrote it down incorrectly. This is what you get, and it's what you need in order for this formula to be true. And this formula is the only one it could be, given that the adjoint is defined to make S dagger S positive. Thank you for catching that. Any other questions or comments? So I want to give an example where you can see in real life that it's true that rho A tensor rho B inverse is well defined, and neither one is separately. And the example will be Rindler space. Let's pick coordinates t that goes up and x that goes left to right. And we could be in two space-time dimensions, but if there are more dimensions, they come out of the blackboard. I'm not giving them names. Then, well, in one of the Zoom lectures, we discussed Rindler space. And we argued, so if psi is the vacuum of a QFT in Minkowski space, we argued that rho u was equal to the exponential of minus 2 pi k right, and rho v was the exponential of minus 2 pi k left, where k right, well, k right and k left are one-sided boost operators. They're supposed to be operators that generate a boost on one side or the other. Perhaps you remember that we got one-sided boost operators because we started in Euclidean space. We needed a rotation generator to sweep out the plane by rotating a ray. We didn't want to rotate a whole line. We wanted to rotate just a ray. You rotate a ray through a 2 pi angle and you sweep out the plane. So that led us to these heuristic formulas. So, well, the full Lorentz boost operator k, which I'll call k, is the integral from minus infinity to infinity dx of x times t0, 0. This is at time 0. All these formulas are at time 0. And it has the property that k is k right minus k left. The reason for, okay, so formally, k right generates a boost in the going forwards in time on the right. And k left generates a boost forwards in time on the left. Now, the reason I put a minus sign in the definition of k left is that the natural boost operator boosts the right forwards in time and the left backwards in time. So, but I'm defining it so that k right and k left are both trying to be positive operators. They've got to be, because the density matrix, it's not allowed to have eigenvalues much bigger than 1. The eigenvalues should be much less than 1. So for the formula to be right, with the minus signs in the exponents, k right and k left should be positive operators. And to try to get positive operators, we boost forwards in time on both sides, which requires a minus sign here. And therefore, there's a minus sign here for the full Lorentz boost operator. Now, the formulas for k right and k left are actually very important but heuristic. K right and k left are not well-defined operators. If you try to ask what happens when, for example, k right acts on the vacuum, you'll find that k right takes you out of Hilbert space. The norm of k right on the vacuum squared would be the expectation value in the state of k right squared. And you could write that as a double integral of the vacuum expectation value of 2 copies of t0, 0. But the integral will be badly divergent near x equals 0. A tell that these formulas can't be literally correct. So what is k right, therefore? K right makes sense as a quadratic form. So it has well-defined matrix elements between suitable states in Hilbert space. For example, in free field theory, k right would have well-defined matrix elements between states in Fock space. So it's well-defined as it has well-defined matrix elements, but it doesn't have eigenvalues and eigenvectors. It's not an observable. It's not a well-defined Hermitian operator that you could measure. A tell that something is wrong with these formulas. Nobody, you all let me get away with it during the Zoom lecture, and maybe I had you all tired out. toward the end of a long Zoom lecture. But I cheated because I didn't do anything to try to make the trace of rho u equals 1. And if we tried to do that, we wouldn't have been able to make sense out of it. So, well, why are k right and k left important, even though they're not rigorously defined? Well, first of all, they are rigorously defined in the sense that matrix elements make sense. And when we discuss the Bekenstein bounds, we will use that. But they're not rigorously defined as operators. But suppose, for example, you're living at very positive x with well-localized states. Then x is approximately a constant for such states. And so k right is approximately your position times the energy. So there are a lot of states where this is well-defined. And if you could treat x as a constant, then k right would be a multiple of the Hamiltonian, and this would have been a thermal density matrix, except that we didn't normalize it by dividing by the partition function, which we couldn't have done, like I just said. But heuristically, at any given x, this is like a thermal density matrix with beta equals 2 pi x. See, the 2 pi is here and the x is here. And therefore, the temperature is 1 over 2 pi x. So heuristically, Rindler space, which means the right wedge, U, is similar to a thermal system with a temperature that's proportional to 1 over x. So these formulas are actually very important, even though they're only heuristic. But from what I've told you, rho u tends to rho v inverse is supposed to be well-defined. Delta psi of region u, which is rho u tends to rho v inverse, is supposed to be well-defined. And one immediate bit of good news you notice is that we don't have to worry about dividing by the partition function, because the partition function is the same for both u and v, so it cancels out in rho u tends to rho v inverse. That's a bit of good news. And even better, you see, using the heuristic formulas here, but the inverse changes the sign, we find that rho u tends to rho v inverse is e to the minus 2 pi times the full Lorentz boost operator. The full Lorentz boost operator is a well-defined Hilbert space operator. It annihilates the vacuum. A quick criterion for whether something is a well-defined operator is whether it maps the vacuum to Hilbert space state. Because every state is similar to the vacuum, except for finitely many excitations, roughly. So the full Lorentz boost operator maps the vacuum to a Hilbert space state, namely 0. And in general, as you perhaps know or perhaps haven't thought carefully about in your study of quantum field theory, K is a well-defined unbounded Hilbert space operator, and likewise e to the minus 2 pi k. So this Tomita-Takasaki theory told us that rho u tends to rho v inverse would be well-defined in a way that the two factors are not separately. And for this special case of Rindler space, we can check it. Any questions on that? Yes?
One question, but the fact that x gets arbitrarily large for x to infinity, so that the boost actually there amounts to a very fast, at least time evolution.
Yes.
That's something that could still create big problems.
Well, it depends on what you're interested in. For what I've... Is the question whether this operator is well-defined? The answer to that is no.
Yeah, simply the fact that indeed, if I have a small excitation and I move it very far away.
Well, you see, this is an unbounded operator, so it's not well-defined on all Hilbert space states. The claim is only that it's well-defined on a dense set of Hilbert space states. For example, in free field theory, it's certainly well-defined on Fock space. So it's not better than that. So you can ask questions where you'd have trouble acting with e to the minus 2 pi k because it is an unbounded operator. However, you would have to think carefully to find trouble. Since it works on Fock space, it works on the states you can describe most easily. Any other questions?
Instead of combining KL and KR, there some way to get rid of the UV divergence of one-sided modular Hamiltonian by considering some the one-sided boost in other states?
Considering what?
Other states.
Well, there is a generalization of this, which I'm about to get to, where we consider two states. So we consider two states, psi and phi, in Hilbert space. And, well, so the goal is to generalize sigma A tensor rho B inverse. So, as I explained at the beginning, I think, we pick psi, which purifies rho A, and phi, let's say, that purifies sigma A. So psi and phi, well, in the finite dimensional setup, psi and phi were in HAB. In quantum field theory, there's only one Hilbert space. There's no HA and HB. And psi and phi are just two states in Hilbert space. But psi is cyclic separating. We don't need to assume that for phi. And you can also generalize the definitions in case psi isn't cyclic separating, just we won't. It's more involved. Now we define the relative Tomita operator. S psi phi is defined by saying that acting on A times psi, it gives back A dagger times phi. So as before, psi being separating makes this well defined, and psi being cyclic means it's defined on a dense set of states. So this is densely defined, and it's unbounded. Unbounded means it's not defined on all Hilbert space states. And then we also have I should specify that this depends on the algebra. Well, we have a Hilbert space with an algebra on it, and we make this definition for all little a's inside the algebra. So it's clearly well defined, at least on a dense set of states. And then S dagger psi phi, we could specify the algebra if we want, is just the adjoint operator. Again, the definition is tricky. You have to, you saw that I even stumbled a little bit. But we use the same definition of the adjoint operator as before. And then we have delta psi phi for this algebra, which is S psi phi dagger times S psi phi. So it's manifestly well defined whenever we have an algebra acting on a Hilbert space. We're given two vectors, psi and phi. Psi is cyclic separating, and phi could be any vector. So it's got to be well defined in quantum field theory. But what is it? So I claim for an ordinary quantum system with Hilbert space AB and state psi and phi in HAB, that delta psi phi for the A system, that means the algebra consists of operators on HA, is sigma B tensored with, sigma A tensored with rho B inverse. So I told you at the beginning of the lecture, well, at the beginning of the lecture we rewrote relative entropy for a finite quantum system in terms of the operator sigma A tensor rho B inverse. And I told you we were going to learn in a little while that it's well defined in quantum field theory. And so in quantum field theory I gave this definition. Goodness, I can't have erased it already, could I? No. I gave this definition here. And the definition on this blackboard manifestly only uses things that exist in quantum field theory. So this delta psi phi is well defined in quantum field theory, and I claim it generalizes sigma A tensor rho B inverse. And it does that by the same computation essentially the same computation we already did. So I won't explain it in as much detail, but I'll write down the beginning. So to check this, in general, psi is something like the sum of ck times k of the A system tensored with k of the B system. Now, phi can be put in the same form, but not with the same basis, of course. So using a different basis, phi is the sum of d alpha. So k runs from 1 to n. Alpha also runs from 1 to n, but it's most convenient to write psi in terms of one basis and phi in terms of the other basis. If you try to refer everything to one basis, one of the two states will look ugly in that basis, and you'll have a mess on your hands. If you are willing to introduce two bases, then you can almost do the same computation as before. You find that S psi phi of alpha of the A system tensored with I of the B system is d alpha over ci bar times I of the A system tensored with alpha of the B system. You find this by the same kind of computation we did when the two states were the same. And then you find out that once you know the formula for S, you can compute delta psi phi, which is S psi phi dagger times S psi phi. And you find that delta psi phi on the state alpha of the A system tensor I of the B system, you find it's an eigenstate with eigenvalue d alpha squared over ci squared. So it's the same computation as before, except that you have to keep track of the two bases. I won't go over it in more detail, but you can find it in my lecture notes if you want to. And then you see from this that delta psi phi is sigma A tensor rho B inverse. Because sigma A acting on alpha multiplies it by d alpha squared, and rho B inverse multiplying on I of the B system multiplies it by 1 over ci squared. So we've succeeded in generalizing this operator to quantum field theory. And therefore, relative entropy makes sense in quantum field theory. What I showed you at the beginning for an ordinary quantum system AB, and with two density matrices, rho A and sigma A, we found that the relative entropy between rho A and sigma A could be defined as minus the expectation value in the state psi. So, psi in HAB purifies rho A. In the explanation, I also introduced a purifying vector for rho B, but for sigma A, but we don't really need it in the formula. The formula we got was minus the logarithm of sigma A tensor rho B inverse. The expectation value of that in the state psi is the relative entropy. So now we immediately know, in the quantum field theory setup, we should define the relative entropy between two states for the region U is minus the expectation value in the first state of the logarithm of delta psi phi. So therefore, in particular, that's a well-defined concept. So this definition is due to Arvaki around 1973 or something, I think. So we've learned that relative entropy in a region, unlike entropy in a region, is well defined in quantum field theory. Yes?
So in this case, if we're talking about the finite dimensional thing,
Yes.
if sigma A, like if one of those d alphas was non-zero and sigma was not invertible, then
Well-
we would have this zero eigenvalue.
Well, it's only for rho, right? A zero of sigma. Oh, sorry. Oh, yeah, sorry. We would. And then the relative entropy would be plus infinity.
Yeah.
It's well defined, but it's valued in real numbers or plus infinity.
Okay.
You see, what Samuel is saying is that sigma A could have a zero, in which case minus log sigma is plus infinity on one vector. And if that vector isn't orthogonal to psi, the value of this is plus infinity. It can't be minus infinity, and we're about to prove it can't be negative. So in the finite dimensional case, relative entropy has two important properties. It's non-negative, and it's monotonic, which in the quantum field theory context means this. If you have a state, an open set U and a bigger open set, if you have a set V and a bigger open set U, U is meant to include V, but it's more, then S psi phi of U is equal to or bigger. Normally it's a strict inequality, but it's at least equal to or bigger than S psi phi of V. So I think I'm going to have to postpone proving the second one until Tuesday, but today we're going to explain the positivity. And when we prove positivity, that will be a new proof of positivity of relative entropy for an ordinary quantum system. Because we've shown that this formula is equivalent to the standard definition for an ordinary quantum system. You might remember we proved it for an ordinary quantum system by first diagonalizing sigma and then comparing to the case where rho is diagonal on the same basis and using positivity in the classical case. So there were a bunch of steps, each of which was elementary. Now we're going to give a different proof, which is valid in quantum field theory, but also in particular is valid in an ordinary quantum system. And we just use the fact that well, let's plot the logarithm function if we plot log x against x, log x is 0 at x equals 1, and it's, I think it's what's called a concave function. I always get confused. It's below the tangent at 1. So log x is equal to or less than x minus 1 for all positive x. So what's true for positive numbers is also true for positive operators. So S psi phi in region U, which is minus the expectation value in psi of the logarithm of delta psi phi. Well, the minus sign makes the inequality go in the opposite direction, so it's equal to or bigger than the expectation value in psi of 1 minus delta psi phi.
So how do you compare operators in the x equals c bar?
Well, a self-adjoint operator can be diagonalized,
All right.
and then whatever is true for each of its eigenvalues is true for the whole operator.
Okay, so it's like because the diagonal on the same basis, you can compare it, right?
Yes, the two. Okay, once we have non-commuting operators, many classical statements are not true. But if we only have one self-adjoint operator, we can diagonalize it and treat each eigenvalue independently.
All right.
So this statement is, think of delta as a diagonal matrix, and then because this statement is true for each eigenvalue separately, it's true for the operators. Now, I probably didn't say this, but we wanted psi and phi to be unit vectors in these definitions. There's a minus sign in front. So if I change the sign here, I get minus log delta psi phi equal to or bigger than 1 minus delta psi phi. Now, let me stipulate that psi and phi are supposed to be unit vectors. If that was implicit in, we assume that in the ordinary quantum case. So we should also assume that here if we want to use this formula. If you want psi and phi to not be unit vectors, you should slightly modify the formula. If psi and phi are unit vectors, then the term with the 1 is just 1. What's the other term? Oh, sorry. This is S dagger S, not S. But you see, the definition of S psi phi was that S psi phi of A psi is A dagger phi. So setting A equals 1, S psi phi of psi is phi. So this is 1 minus phi phi, which is 0. So we've proved the positivity of relative entropy in a form that's valid both in quantum field theory, where you're considering a region, and in ordinary quantum mechanics, where you're considering any subsystem. Now, as I've told you about 8 times, monotonicity of relative entropy, first proved by Lieb and Ruskay around 1972 or something, is a much deeper statement. And we're all set up so we'll be able to give a simple proof on Tuesday for the case of comparing a region to a bigger region. If you want to be prepared for that, you could read about it in section 3 of my lecture notes, the ones which are called notes on some entanglement properties. The proof of Riesz-Leiter was in section 2 of there, as I've mentioned a couple times. And what I've said today is in sections 3 and 4, a synopsis of things in there. You could find much more detail in the written version. But the proof of monotonicity in enlarging a region is definitely in section 3. And in section 3, you'll find I first give a heuristic explanation, and then I give the rigorous proof. In planning the lecture last night, well, obviously, I'll tell you what happened, but we didn't get to the proof anyway. I first planned to give the rigorous version. But then after a while, I first planned to give the heuristic version on the grounds it was more elementary. Then I decided the rigorous version was actually shorter than the more elementary version. So then I prepared to explain the rigorous version in the lecture. And I think that's what I'll actually do Tuesday. So if you want to read the heuristic explanation, you'll have to look at the lecture notes. So that's it for today, but we do have about a minute or two for questions if there are any.
So here you place the V set inside a U.
Yes.
Could you give say anything about like relative entropy of sets?
Well, the only simple statement is that when you make a set bigger, you make the relative entropy bigger. Let me remind you of the statement in quantum mechanics. In quantum mechanics, the statement is that S of rho AB relative to sigma AB is equal to or bigger than S of rho A relative to sigma A. And also classically we actually proved the corresponding statement. In quantum mechanics, we haven't proved it. Classically, we proved it in one of the Zoom lectures where we introduced these things. So when you make a system bigger, you make the relative entropy bigger. So a natural setup in quantum field theory is to consider a region and a bigger region containing it. Yes?
Yeah, so the sign here is assumed to be cyclic separating.
Yes. Phi is any state.
Yeah, and phi can be any operator. For example, can be obtained by acting with operators.
Phi is any state.
Phi is any state.
Yes.
There's no restriction.
It should be a normalizable Hilbert space state.
So only the psi is required for the sign.
Yes. But another fact, you see, in ordinary quantum mechanics, cyclic separating means the density matrix is invertible. And that's true for a generic density matrix, assuming the dimensions of the two systems are equal. So analogously, in quantum field theory, once you know that there is a cyclic separating vector, such as the vacuum, almost all states are cyclic separating. So it's a mild condition. That's one fact, but another fact is that I shortened the lecture, and also my lecture notes, by only giving definitions in the cyclic separating case for one of the vectors. But you can generalize the definitions. Any other questions? Yes?
So I guess so in this quantum field theory case, if phi is generically also cyclic separating, will you not run into this divergence?
Not necessarily.
Yeah. Okay, you can
No. It's hard to say what's generic, but there are an awful lot of states where relative entropy is finite. Relative entropy being infinite means that it's very, very easy to distinguish the two states by measurements. See, I don't know, if you take the vacuum and then you take some other state, it contains some excitations. But a measurement isn't going to tell you with certainty that your state isn't the vacuum, because whatever fluctuation you observe could have happened in the vacuum. So relative entropy being infinite means that you might be able to learn after a finite number of measurements with certainty that the two states are different. And you could figure out how to do that in quantum field theory, but it's a little bit unusual. It won't happen, you won't get that unless you think about it carefully. Any other questions? Oh, yes?
So for algebra that we get from completing from A naught by
Yes.
using a certain Hamiltonian,
Yes.
if it doesn't have an irreducible representation in the Hamiltonian, in the Hilbert space, does it mean it's unbounded? Does it make sense?
Well, I mean, there are various questions here. In quantum statistical mechanics in infinite volume, the Hamiltonian's always unbounded. Right. In fact, it's typical energy. The energy is usually a multiple of the volume. So a typical state at positive temperature has infinite energy and infinite volume. So that's one statement answering your question.
So what caused it doesn't have irreducible representation?
Well, I didn't give an abstract proof on Tuesday, but we saw that when we constructed the algebra, it didn't. In other words, if we tried to work in the original Hilbert space, where you would think the algebra acts irreducibly, the original Hilbert space doesn't have the typical excited states at temperature T, because excited states at temperature, the original Hilbert space was separable, countable dimension. To describe all the typical states at temperature T, you would have needed a Hilbert space of uncountable dimension. Then we were able to describe statistical mechanics in a separable Hilbert space by passing to the thermofield double. But that caused the representation to be non-irreducible because we had to introduce a second copy of the system. I didn't really give an abstract proof. I just showed what works. And what worked made the algebra act highly non-irreducibly. Namely, we introduced a second algebra that acted on the second copy. Any other questions? Okay, if there aren't questions, then on Tuesday we'll start with monotonicity of relative entropy under enlarging a region. And then I think we'll discuss the Bekenstein bounds.